Hey everyone, welcome back to ResICon 313. In this video, I will talk about Chapter 13, Information Gathering. Chapter 13 is about information gathering, and we will talk about 3 topics for this chapter. The first topic is how to evaluate if information is useful or not. Okay. The second topic is how to put a value on imperfect information. We have done this before. We have put a value on perfect information or clear ones in the previous chapters. In this chapter, we look further into that topic to look at what if the information we get is not 100% accurate as a clear one would be able to provide. How do you put a value on those kind of information? And lastly, we'll summarize the principles of information gathering. If information is proved to be useful and material, how would you gather information like that? Okay. So the first thing about information gathering is that to recognize that most information we can gather in the real world is not perfect. We don't have a clear want, or we cannot get clear wants in real life. That is just an imaginary figure that we created to be able to give us some starting point to analyze information, the value of information. As you can imagine, if you have imperfect information, the value of the imperfect information is definitely going to be lower than the value of perfect information. Okay, so in that sense, the value of perfect information give us the higher bar that in terms of in the scheme of values of information when it goes from perfect to imperfect. Okay, now we will look at how we can distinguish between useful and wasteful information. And we will put a value on useful but imperfect information. And this is actually one of the most useful features of our class. Okay. So the first topic we're going to cover is to distinguish between useful and wasteful information. So we use tools that we have already developed and learned within this class to do that. When we determine whether information is useful or not, we can look at either probability tree or relevance diagram to make that judgment. Okay. So in here, we'll make the differentiation between assessed form and inferential form probability tree or relevance diagrams. So essentially, we're going to see what is a probability tree of the assessed form. We'll look at what is a probability tree of the inferential form. We'll also look at diagrams, relevance diagrams of the assessed form or of the inferential form. Okay. So in order to begin to do that, we need to first classify the distinctions in our, in our eyesight or in our view into distinction of interest and distinction of observed distinction. Here in the party problem, the distinction of our interest, what we really care about is how the weather is going to be on the party day. So that is our distinction of interest in the party problem. This distinction of interest is essentially what you want to know and what matters in your decision problem. On the other hand, the observed distinction is something you can observe and infer information from, and to make judgment on the distinction of interest. So for example, in the party problem, the observed distinction would be maybe a rain detector or the clairvoyance message. Okay. So this is what you can run experiments on and decide how accurately the detector can predict the weather or how accurately the clairvoyant can predict the weather. So you can, from past experiences, you can experiment on how accurate these detectors are. That is the information gathering part. Based on those information, you can decide how you can infer the weather information from the message of the detector. So the value of the observed distinction comes from its relevance to the distinction of interest. Again, think about an observed distinction like a coin toss. Everyone is clear that the result of the coin toss is irrelevant to the likelihood of the weather being rainy or sunny. So you would never pay to read the result of a coin toss if you're interested in predicting what the weather will be like in a certain day, someday in the future on the party, when the party is going to be held. Okay. So when we say that whether an observed distinction is useful or not to predict the distinction of interest, apparently we can do that in two ways. We can either use the relevance diagram, or we can use probability trace to evaluate the relevance relationship, right? These are the two methods that we have already learned in order to decide whether one distinction is relevant to another. In the probability trace, we'll compare the conditional probabilities, and if they are the same based on different observations, then the observed distinction is irrelevant. Versus in the relevance diagram, we observe the irrelevance relationship by observing whether there is an error between two distinctions or not. Okay, so let's start with an example. Suppose that, again, we're looking at the party problem. So we have a rain detector that we have already experimented on, or some reliable institution that studies rain detectors have already experimented with the rain detector for us. Either case, this is what we know. We observed that in the 100 days during which we experiment, we try to evaluate the accuracy of the detector. Now we did that for 100 days, and during these 100 days, it turns out that we have 40 days of sunshine and we had 60 days of rain. Okay, and in the 100 days of experiments, among the 40 sunny days, the detector was able to predict that in 32 days, meaning when the weather is actually sunny, the detector said sunny in 32 days. And in the other 8 days, the detector read rainy. Okay? And then among the 60 rainy days, the detector reads rainy in 48 days, meaning and then for the remaining 12 days that it actually rained, the detector falsely predicted it to be sunny. Okay, so these are the results from our experiments in the last 100 days experimenting with the rain detector. One thing that is perfect clear now is that the rain detector is not 100% accurate. When it is going to be sunny, the detector was only able to predict it 32 out of the 40 days. When the weather is actually raining, the detector is only able to predict 48 of the 60 days. Okay, so these are the information that we have gathered so far in terms of how accurate the rain detector is. And the first step we want to do is to represent these results in a probability tree. Okay, so if you think about the first result, this represents the general probability of sunshine and raining. in this area, right? This is without any messages from the rain detector. We know that 40% of the days that we experimented, it's going to be sunny. It was sunny, and 60% of it was rainy. And this actually represents a conditional probability. Conditional on the weather being sunny, how likely the rain detector is going to predict it's sunny. This represents conditional on the days are actually rainy days, how often the detector can predict it. Okay, given this information, we'll be able to draw the probability tree like this. So as you can see, without any other information based only on our experiences from the experiment, 40% of the chance it will be a sunny day and 60% of the chance it's a rainy day. This is without reading any detector's message or without consulting anyone that knows more information on the weather. And of the 40 days of sunny, of the 40 sunny days, 32 days the rain detector is predicting it's sunny. So 32 over 40, that gives us an 80% of conditional probability that conditional on the weather being sunny, the rain detector with sunny. Okay, here again, as our convention that we have already always been using, we use the quote to tell people that this is a message from some kind of rain detector or other information providing services. Okay, and like I said, 32 days the detector said sunny, and then the other 8 days the detector falsely predict it's a rainy day. So 8 over 40 is 20%. Okay, and then among the 60 rainy days, 48 days the rain detector said rainy. So the 48 divided by 60 is 80%. And then in the other 12 days of rainy day, the detector actually read sunny, which is incorrect. But 12 over 60 is the 20% over here. And at the end, these are just the elemental probabilities. So this is it, a probability tree that have gathered or have organized the information that we have from the experimenting process with the rain detector. Okay, so this is the probability tree. As we have learned before, we can use a relevance diagram to represent this probability tree like this. So weather is our distinction of interest. We are interested in the weather. Detector is the observed distinction. We are able to observe a message from the rain detector before the day of the party, which we can use to predict the weather of the party day. Okay. Observed distinction, the value of it comes from the ability that it is relevant to the observed distinction, and we can use the information from the observed distinction to predict what would happen on the distinction of interest. Okay. So here, the distinction of interest comes in the first, in terms of the order in the probability tree, and the observed distinction comes as the second distinction in the probability tree. And apparently, weather is relevant to the detector's message. The reason is that S quote given S is 0.8, S quote given R is 0.2. These two conditional probabilities are different. So we know that weather is relevant to the message from the rain detector. Again, if you're confused with how to do this, refer back to the chapter where we talk about relevance. Okay, and then we use an arrow to go from weather to detector to represent that relevance diagram that relevance relationship. We call the probability tree with an order such that distinction of interest goes first, observed distinction goes second as the assessed form probability tree. And also we call the corresponding relevance diagram as the assessed form relevance diagram. Okay, so the assessed form probability tree or distinction or a relevance diagram represent this experimenting process. So this experimenting process is useful to tell us something about the accuracy of the rain detector when predicting weather. When predicting whether it is going to be rainy or not on a specific day. However, if we were to use the message from the detector in our decision diagram or in our decision process, this is what we will be looking at, right? We looked at this decision diagram with clairvoyance before, but now we're interested in looking at this decision process with this specific rain detector. So the order of the decision, if you decide to buy the rain detector or rent it, it will be first you read the message from the rain detector. Based on the message, you choose the party location, outdoor, porch, or indoor. This is what you would choose after you get a message of sunny. This is where you would choose given a message of rainy. And then still you choose the location after you read the message, but before the party day. Okay, after you choose the location, the party day arrives, and then you get to experience the day as either sunny or rainy as it turned out to be. Okay. So we have done this with clairvoyance where we figured these two probabilities based on a tree reversal. So this is what we're going to do with the rain detector as well. However, if you look at this decision diagram, what matters here are these probabilities over here and these two probability over here. Okay, so this is the probability of a detector giving a sanity message. This is the probability that the detector gives a rainy day message. This is the probability that the weather is actually going to be sunny when you get a message of sunny, when you get a read of sunny day from the rain detector. So as it is pretty clear, the order between the observed distinction and the distinction of interest is not the same as in the probability tree that we have drawn before, which is referred to as the assessed form probability tree. As you may already predict what will be the next step, we will need to reverse this tree to get these probabilities that we need to analyze our decision over here. Okay, so this is about how much information about the weather that we are actually going to be able to infer from the detector. If the detector says it's a sunny day, how reliable is that? Okay, given that the detector says sunny, what is the probability that the weather is actually going to be sunny? And if the detector says rainy, what is the probability that the weather is actually going to be rainy? Okay, so these are the two probabilities that we are talking about. This first one is conditional on a sunny day message. What is the probability of a sunny weather? Conditional on a rainy day message. What is the probability that the weather is actually rainy? Okay. So in order to get these two probability trees, we cannot use the assessed form. We need to reverse the assessed form probability tree into such an order that the message comes first and then the weather comes second. We need to reverse it. Okay. And there are 4 steps of it that we have repeated so many times. So in the interest of time, I'm just giving you the result here. Okay. As you can see, after we reverse this assessed form probability tree, we got another probability tree where the observed distinction comes first and the distinction of interest comes second. Okay. And if we use the diagram, the relevance diagram, to represent this reversed tree, we would just reverse the arrow. Detector message comes first. Weather is conditional on the detector's message. Probability of weather is conditional on the message from the rain detector. As you can see, given different messages from the rain detector, the probability that you would assign to the day being sunny is different, right? So these are the probabilities that we're going to substitute into the the decision tree that I have shown in the previous slide. And now with this probability tree, we are able to answer the 2 questions that we have posed before. And this first, I want to point it out that this reversed order probability tree is called the probability tree of the inferential form. Okay. The name inferential form comes from the fact that in this order, we're trying to infer the weather from the message, hence the name inferential. Also, if you look at the relevance diagram, where the distinction, the observed distinction, is sending an arrow to the distinction of interest, this is the relevance diagram of the inferential form. Like generally over here, this is the general form of it. You go from the observed distinction to the distinction of interest. Versus before, with the assessed form probability tree or relevance diagram, you go from distinction of interest and send an arrow to the observed distinction. Now, to answer these 2 questions, given it's a sunny day message, the probability that the weather is actually sunny is only 0.727. Given the message is rainy, the probability that it is actually going to be a rainy day is 85.7%. Okay. These 2 are not the 2 these 2 questions are not the only questions we will be answered from looking at this probability tree. Here, 27.3% of the chance that the weather is going to be a rainy day, even with a message of a sunny day. Okay, here you can read that. You can read this too. These 2 numbers, these 2 probabilities represent how likely you are going to get a sunny day message, how likely you are going to get a rainy day message without any other information, because this is the first distinction over here. So what we have gone through here is just an example of a pair of distinction of interest and observed distinction. And there are other examples that you can think of where the first pair could be you're interested in whether oil is underground in a certain area before you set up a development to drill oil in this area. What you can do is you can use some kind of test to detect whether there is oil underground or not. This is cheaper than setting up a drilling development to actually start to drill. So you want this first. If you're a manager of the firm, you're interested in how much product you should produce for the future market. And in that decision, you're interested in the amount of sales that you can make for a product. Then before putting in the resources to produce the products, what you want to do is to do a cheaper test, which is a market survey, to test if people are really interested in your product. These surveys only provide you with some information. people taking the survey indicate their interest, but there is some chance that someone who said they're going to buy will not buy in the future. Someone who said they will not buy will actually buy it when the product becomes available. So, these surveys are the detectors of people's interest, which may not be 100% accurate since, it's just a survey. You're not asking them to put down the money a sort of deposit for your product. And then a very popular example that you may have already encountered in your statistics class is the pair, such that the distinction of interest is whether a person has a certain disease, and the observed distinction could be a medical test, whether it's a simple test to say whether the person could have the disease or not before you actually treat that person with the treatment for that specific disease. The reason being that when you treat a disease, it's usually expensive and usually have side effects. You don't want to rush into that before having some kind of indicator whether this person have disease or not, in addition to the symptoms. And usually the medical tests are very accurate. However, it's never 100% accurate. I don't know any kind of accurate medical test like that. And then there are the cost prediction element too. This is a summary of what we have learned so far. We have looked at the relevance diagram of the assessed form, the probability tree of the assessed form. We have looked at the relevance diagram of the inferential form, or the probability tree of the inferential form. When we look at anything of these two, any of these two that are in the assessed form, it starts with the distinction of interest, and then it ends with the observed distinction. These probabilities, with the arrow over here, the probabilities represented by this oval will be the conditional probability of the observed distinction conditional on the distinction of interest. We call this type of conditional probability the likelihood. It's just another fancy name to refer to the conditional probability of the observed distinction on the distinction of interest. Versus in the inferential form, we're trying to infer information from observed distinction to predict the distinction of interest. And here, this round or this oval-shaped distinction represent the conditional probability of the distinction of interest conditional on the message from the observed distinction. We call this type of conditional probability the posterior. Okay, this is just another name to refer to this conditional probability over here. And some other terminologies in addition to likelihood or posterior here, we have already. This is the probability of the distinction of interest in the assessed form is called the prior. It means prior to read the observed distinction, what is your probability assignment to the distinction of interest, to different possibilities of the distinction of interest. Okay, over here we have already defined this is the likelihood. That is conditional on different possibilities of the distinctions of interest. What is the likelihood of different messages from what is the likelihood of receiving different messages from the observed distinction? And this one, the observed distinction, the probabilities of different possibilities for the observed distinction are referred to as pre-posterior. Okay, this is the likelihood of getting different messages from the observed distinction without any other information. And this is what we defined before. the posterior. That is, this is actually the how reliable you can infer information from the observed distinctions. Given different observations of the observed distinction, what are the likelihood, or I'm sorry, what are the probabilities for different possibilities of the distinction of interest? So prior to likelihood in our assessed form, then reverse assessed form, we have pre-posterior and posterior. You can sort of the name pre-posterior is because this is before the posterior probability. So applying, using these terms and connect these terms with the example that we saw before. So here in the assessed form, we have prior and likelihood. So the prior would be these two probabilities, okay? Prior to read the message, how likely is the weather going to be sunny? How likely is the weather going to be rainy day? These two probabilities are represented by this weather distinction in the assessed form. Then the oval in the assessed form that represents the observed distinction represent the likelihood, okay? So that are these four probabilities over here. They are all referred to as the likelihood. Okay, you can read the meaning, you can interpret the meaning of these four conditional probabilities based on our previous classes. I will skip that part now. Okay, priors and likelihood, prior probabilities and likelihood probabilities can only be found in the assessed form probability tree or relevance diagram. There is no prior or likelihood in the inferential form, okay? In the inferential form, we have pre-posterior and posterior probabilities. Okay, over here, the pre-posterior probability is the probability of the messages in the detector in the inferential form. That would be the two probabilities over here. Okay, without any prior knowledge, without any other knowledge of the weather, how likely are you going to receive a sunny day message? How likely are you going to receive a rainy day message? And then this is posterior, which refers to the four probabilities over here. If you get a sunny day message, what is your posterior probability that it is going to be a sunny day? If you receive a sunny day message, what is your posterior belief that it actually is going to be a rainy day? That's how we use the term in a sentence. These elemental probabilities, we don't have names for them. Okay. Next, among the probabilities in the likelihood category, among these four probabilities, we have two other names to refer to this probability and to refer to this probability. Okay. So think about this. We're talking about a rain detector. If the message is rainy day, that's a positive. If the message is a sunny day, that is a negative. This is a rain detector. This is not a sun detector. Okay. So in that sense, this probability of predicting a true positive is called the sensitivity. This probability that the detector is going to be able to predict a true negative is called specificity. Positive means rain. Negative means opposite of rain, which is sunny. Okay. This sensitivity tells us how accurately the rain detector is going to be able to predict a rainy day. This specificity tells us how accurately the rain detector is going to predict the negative of rain, which is sunny. Okay? These two numbers do not have to be the same. we may have rain detectors that are pretty good at predicting rain, but not so good at predicting the negative of rain. So imagine that there may be such a rain detector that the sensitivity is pretty high, 0.9, versus the specificity is only 0.5. Okay. So these two numbers don't have to be the same. The sensitivity and the specificity don't have to be the same. When they are the same, we can refer to these two terms in a unified term called accuracy. Accuracy can only be used when these two numbers are the same, when, or equivalently, when the specificity and the sensitivity of any detector is the same. That is when you can use accuracy to refer to both in a united way. Well, actually, this assessed form and inferential form probability trees are not strange to you. We have done this before with clairvoyant, right? You can think of clairvoyant as such a detector that has 100% accuracy. So this is the assessed form probability tree for clairvoyant message. You know, the prior probabilities are the same because we're still looking at the weather of the same region. But when it is going to be when the days are sunny, the clairvoyant was able to predict it with 100% of specificity. When the weather is rainy, the clairvoyant was able to predict that with 100% sensitivity. Okay, and since the specificity and sensitivity are the same for clairvoyant, we refer to these two as the accuracy. So clairvoyant has 100% accuracy in predicting the weather. That is what we learned from the assessed form probability tree. And we have already done this before when we try to value perfect information or when we try to value clairvoyance. We reversed the tree so that the clairvoyance message comes first and the weather comes second. And as it turned out to be that when the clairvoyant says it's going to be a sunny day, 100% of the chance it's going to be a sunny day. When the clairvoyant says it's going to be a rainy day, 100% of the time it's going to be a rainy day. So clairvoyant's message are 100% reliable because clairvoyant has a 100% accuracy. Okay, all these numbers come from the steps of reversing this probability tree into this order. Now with the terms that we introduced in this class, we can say that the probability tree over here is the assessed form probability tree for clairvoyant. This is the inferential form probability tree for clairvoyant. Again, prior probabilities, likelihoods, pre-posterior, posterior probabilities. That is how we use those four terms to refer to probabilities in these two trees. Okay. As you can say that when we have some kind of a detector that has the same sensitivity with the specificity, we can refer to these two as the accuracy. Okay, so we're now going to look at this special type of detector that has the same sensitivity and specificity. So this is the detector that we introduced in today's class that has an 80% of accuracy in predicting weather. And this is what we saw before, right? 80% of accuracy. And after we reverse the tree, we can look at this posterior. And when P is equal to 1, we have clairvoyance. And then we're referring this and the posterior. Okay, like I said before, clairvoyant is just 100% accurate weather detector. And both the detector and clairvoyant provides useful information because both of them are relevant to the distinction of the weather. As you can see, as you can imagine, we may have other rain detectors that have 70% of accuracy, 90%, or 85%. So no matter what the accuracy is, you can use the assessed form and inferential form probability tree to infer information from that detector. As it turns out, that there are these are the ways that you can, these are the things you need to pay attention to when you try to distinguish between useful and wasteful information. First thing is, of course, still you need to be clear about what is your distinction of interest and what is your observed distinction. That's the first step for you to begin to draw the assessed form probability tree and then to reverse it to get the inferential form probability tree. Then you can experiment you can experiment to get the connection between these two distinctions. That is when you use the assessed form probability tree to look at the prior probabilities and likelihood probabilities. Then when you are looking at some time in the future, you can reverse the assessed form probability tree to get the inferential form probability tree. That's how you get the pre-posterior probabilities and the posterior probabilities. So the experimenting and assessing process happens in the FAST, where you are able to verify the different possibilities of the distinction of interest and then connect it to how the observed distinction is going to behave. Then, based on your past experience, you can predict the future. So this is past, this is in the future. Another example that I mentioned before is the testing for a virus, okay? So here is the general belief, the prior belief, meaning the belief about people's likelihood of infection prior to reading the test. This is what we've gathered so far in the maybe past year or for the current situation since the coronavirus began to develop. We have already observed that generally in the population, 1 out of 400 people are sick or actually infected. So we can represent this observation or this experience with the probabilities that we call prior belief. So given background knowledge, 1 in 400 people get the virus and the other 399 people do not. Okay, and the virus versus no virus are the two possibilities of the distinction of interest, which is the virus infection status of a person. Then you develop this test. If a person is infected, then 99% of the chance that the test is going to say that the person is infected. On the other hand, if a person is not infected, 99% of the chance that the test will indicate that the person is not infected. Here, the term positive, negative is very naturally applied. Positive for infection, negative meaning no infection. Okay, this 99% over here is the sensitivity of the virus test. This 99% of the chance is the specificity of the virus test. Since these two are the same, we say that the test has a 99% accuracy. If this number and this number is not the same, if this is 99% and this is 80%, then we cannot use the term accuracy to describe this test. The accuracy term only works when the test has the same specificity and sensitivity. Now the question that we're interested to ask is, now suppose you have taken the test and you get a positive result. What is the probability that you actually are infected by the virus? There is a chance that you may not be infected, even the test result is positive, because it's not 100% accurate. In order to do this, we start with the assessed form probability tree. In the assessed form probability tree, we put the priors and the likelihoods into position. Here, without any background, with only background knowledge, 1 in 40 get the virus, 399 don't. When a person get virus, 99% of the chance the test is going to say the person get the virus. That is 99% of the chance the person get a positive result. There's still 1% of the chance that the test failed to predict to say that the person has a virus. And then over here, when a person doesn't have a virus, 99% of the chance that the test will turn out negative. Still, there's a 1% of the chance that there's a false prediction of positive over here. Okay, sensitivity, specificity, they are the same. They're referred to as accuracy. These are the priors. These are the likelihoods. Again, specificity and sensitivity and accuracy are just special types of likelihood probabilities. Now, what we just did are filling in what we know. We have prior probabilities on the disease. We have the likelihood, which gives us the conditional probabilities of the test, conditional on the actual presence or not of the disease. And now what we need to do in order to answer the question is to reverse the probability tree into this inferential form. Here, test result comes first. Actual disease comes second. This is the inferential form. Test first, virus second. And here are just the steps to do it. First, reverse the order, and second, match up elemental probabilities. The third step are to get the marginal probabilities, and last step is to get the conditional probabilities. Here I have already provided all the necessary formulas. Over here, if you don't understand, you need to refer back to the chapter where these are introduced. So after we do this, we're able to answer the question we posed to begin with. If you get a positive result, what is the probability that you actually have the virus? Okay, so this is a conditional probability. What you're interested in is the probability that you have the virus. What you know at this point is that you have already got a positive result. So as you can see, this is the probability over here. Given that you have a positive result, 20% of the chance you have the virus. Okay. As a matter of fact, despite of the test being very accurate, 99%, because of the low probability of virus in the prior, even if you got a positive result, there's only a 20% of likelihood that you are actually carrying the virus. And despite of the positive result, 80% of the chance that you are not carrying the virus. Now we can also ask this question. If you get a negative result, how reliable is that? If you get a negative result, how likely is it that you are indeed negative of the, you are indeed virus-free? The probability is over here. As it turns out, if you get a negative result, 99.9975% of the chance you don't have the virus. So as it turns out, the negative result is pretty reliable. The reason is, again, because in the prior, only 1 out of 400 people are infected by the disease. Okay, so this is how we determine the usefulness, or how we can infer information from imperfect information, from the imperfect rain detector, from the imperfect disease. The next question is, how do we put a value on the imperfect information? Well, the way to do that is very similar to the way we put value on perfect information. So again, we're going to use the party example here. This is what we learned before. Without clairvoyance, without rain detector, without any detector for the weather, this is the party problem. And indoors is the best option for Kim. That is equivalent to a $46 value of a party. And we analyzed before the clairvoyant, which is a 100% accurate rain detector. We asked the question, should Kim pay $15 to get the clairvoyant message? And this is what we did. Okay. This is what we did before, just a quick review. So as you can see, this is the inferential probability tree for the clairvoyant. And we have used the information or the probabilities in this inferential probability tree to plug them into position in the decision diagram. Here, these two probabilities are plugged in over here, representing the probability of a sunny and rainy day given a sunny day message. Okay, these two. And then these numbers come from here, another set of posterior beliefs post to a message after receiving a message of rainy day. After receiving a message of rainy day, what is the probability that the weather is sunny or rainy? And the pre-posteriors are marked over here, meaning how likely do you get a rainy day, sunny day message and a rainy day message. This is what we already covered before in the previous chapter. Look at the recordings if you don't understand. And we know that we analyzed the decision problem like that. And we figured the value of party after purchase is $51. Since it's higher than $46, Kim should buy clairvoyance at $15. And the way to figure out the maximum price that Kim is willing to pay to get clairvoyance is by increasing $15 to $16 to $17 going forward. And if we know Kim is a Delta person, you can start with free clairvoyance and then take the difference between value of the party with free clairvoyance and value of party without clairvoyance. This is, again, something we learned in the previous chapter. So this is what we learned before. We're going to follow the similar steps to analyze what is Kim's willingness to pay for the 80% accurate rain detector. The way to do that is, well, let's say the question we want to ask is Kim willing to pay $10 to get the rain detector that is only 80% accurate? So is the information from the detector useful? We have already answered this question. The two are relevant to each other, so it is helpful. And then what we need to do is to get the value of the party problem after paying $10 to read the detector. start with the assess form, and already we got the inferential form. What we need to do is to plug these probabilities to the decision problem tree, just like what we did for the clairvoyance. Okay, so this is the inferential probability tree that has the pre-posterior, that has the posterior. Then what we want to do is to get these two probabilities. What are these two probabilities? These come from the fact that all this come from this branch, which means a sanity message. So given a sanity message, how likely is the weather being sunny? How likely is the weather being rainy after choosing outdoor? We know the choice of the location doesn't affect the probability of the weather. So these three numbers are the same, and these three numbers are the same, and they all come from this part. Sunny day given a sanity message. Rainy day given a sanity message. 0.727, 0.273. And then these probabilities represent the probabilities of sunny and rainy after receiving a rainy day message. And you can find that over here in this set of posterior beliefs. Given it's a rainy day, 14.3% of the chance it is going to be a sunny day. 85.7% of the chance it's going to be a rainy day. You know, that's over here. Again, the choice of location doesn't affect the probability of the weather. The weather, Kim is not cursed. It doesn't work like if Kim choose outdoor, the weather is going to be more likely a rainy day. Doesn't go like that. And then the likelihood of receiving sunny and rainy day message are the pre-posterior. So these two numbers are these two numbers. So every piece of information or every probability in the inferential probability tree can be used in this decision problem, except for the elemental probabilities. We really don't use that in the decision problem over here. And after we plug in these probabilities, the next step is to get the values, okay? So this is what Kim would do without clairvoyance, without rain detector. We're comparing with or without rain detector. This is what happens without rain detector. This is what happens with rain detector for $10. Again, you need to subtract $10 from the value of the party. You need to get the U values of the value of the party, value of different prospects after subtracting $10. Then you need to figure out the values for these 6 nodes. Okay, over here, unlike the situation for clairvoyance, what comes after this node is an actual uncertain deal, versus before, what comes after this is a certain deal of 100% sunny for clairvoyant. We're not looking at clairvoyant now. We're looking at a rain detector. So you still have some uncertainties about the weather, even after you receive a sunny day message. For clairvoyant, you do not have any uncertainty about the weather if you receive a sunny day message from the clairvoyant. That's the difference. That's why you need to go through the U curve of Kim in order to figure out the U value of this uncertain deal. Over here, we're taking a different approach. Instead of putting the dollar values over here, let's just simply put the U values of this uncertain deal, this uncertain deal, this uncertain deal. Again, the U value of an uncertain deal is probability of a sunny day times the U value of a sunny day party after paying $10. And this times this, that gives you this number, and this number, all these numbers. And you pick the best alternative, which has the highest certainty equivalent, or that has the highest U value. So as it turns out, if the rain detector says it's a sunny day, porch is the best option. And if the detector says it's a rainy day message, indoor is the best option. Okay. If the detector says rainy day, the choice on the party location is the same without. But if the rain detector says it's a sunny day, the choice is porch. If you recall, when the clairvoyant says it's a sunny day, the choice is outdoor. Again, because there's no uncertainty over here and the outdoor has the highest value. Over here, when the detector says it's a sunny day, there are still some uncertainties about the weather, which makes porch a more attractive option than the outdoor option. And then the U value of this decision is 0.6797. The U value of this decision part is 0.551. Then the value of this decision problem is 0.44 times 0.697 plus 0.56 times 0.557. That gives a U value of 0.615. Okay, again, so this 0.615 is equal to 0.44 times 0.697 plus 0.56 times 0.551. So this is how you get the U value over here. This 0.1615. And then you need to go to Kim's U curve and figure out what amount of dollars correspond to a U value of 0.615. That will give you $44.65. Since this is lower than the value of the party without rain detector, the answer is $10 is not worth it. Now, how about $9? How about $8? So you need to decrease the $10 to a lower number until you find that this number is equal to this number. That gives you the maximum price that Kim is willing to pay for the rain detector. Okay. As it becomes very clear that for an 80% accurate rain detector, $10, even at $10, Kim would not be willing to pay for it. And as we analyzed before, Kim's maximum willingness to pay for clairvoyance is way higher than this $10. This again tells us that the value of imperfect information should be lower than the value of perfect information. Okay. So this is how we analyze Kim's problem. This is provided that we do not know Kim is a Delta person. We need to use the trial and error method. If we do know Kim is a Delta person, we can start this with paying $0 for the rain detector. Get the certainty equivalent over here. Subtract this number from that certainty equivalent. That is the maximum willingness to pay for the rain detector if we know Kim is Delta person. Okay. Again, we're going to analyze the situation for Jen and the same rain detector. Now it has a name. It's called Acme rain detector. The same rain detector of 80% accuracy, and Jen is risk neutral and has all the other same prior beliefs about the weather, and has the same dollar values to the parties. Now the question is, what is the maximum price that Jen would be willing to pay for this Acme rain detector? Okay, to do that, we know that Jen is risk neutral. That means Jen is a Delta person. So we can start with free clairvoyance, okay? And these numbers are the same with Kim's. So these two numbers are actually wrong. Let me correct that. Okay, I have made the correction. So like I said, Jane has the same beliefs as Kim in terms of the pre-posterior and the posterior. So all these numbers are the same with Kim. But since Jane is risk neutral, Jane's value of the party without this should be dollars over here. Jane's is $46. I'm sorry, Kim's was $46, but Jane's is $48. Again, this was introduced before. Have to get this $48. Then we need to find out Jane's value of the party with free, not clairvoyance, with free ring detector. So this is what happens if Jane gets the free ring detector. What we need to do is to put a value over here and then take the difference between these two values. That will be Jane's willingness to pay for the ring detector. So again, we start from the back. Since it's a free ring detector, no cost is deducted from over here. And then Jane is risk neutral. So Jane's value of this uncertain deal is just the expected value of this uncertain deal. We do not need to use U-curve or U-function to figure out Jane's value of this uncertain deal. So 72.7% times $100 plus 27.3% times $0, you got $72.7. Similarly, over here, you got 70.942, so on and so forth. So as it turns out, if the message is sunny day, Jane would choose outdoor. If the message is rainy day, Jane would choose indoor, okay? So the value of this decision is 72.7. Again, the highest certainty equivalent of the options. And then this is 48.6. Then the value of this uncertain deal is the expected value of it, which is 0.44 times 72.7 plus 0.56 times 48.6. So we got it here by using okay. Again, this is the expected value of the deal. We are able to do this because Jane is risk neutral. So now we have figured out that Jane's value of the party with free ring detector is 59.2. Now, since Jane is a risk neutral person, her value of the imperfect information from the Acme ring detector is the value with free ring detector minus the value without ring detector, which is $11.2. This is again a typo. You can take the difference because Jane is risk neutral, which means Jane is a delta person. You cannot do this if Jane is not risk neutral or not a delta person. And no utility graph is needed, again, because Jane is risk neutral. Okay, so this is how we can analyze the value of imperfect information for a specific decision problem for different people with different risk attitudes. Again, the inferential probabilities. The probabilities in the inferential probability tree are the key here. However, you cannot get the probabilities in the inferential probability tree unless you have done the experiment and completed the assessed form probability tree. Okay, that's how everything is connected together.